So welcome to the last part of lecture 3. So in the last part, we talked about taking subsets and then adding them together to make it build something bigger. Now, what we want to do in this last part is kind of explore what happens if we took a bunch of subspaces and started added them together. And what we'll find is when we take subspaces and take their sum, we continue to have a subspace. So really, I just had my intention in this last part is really to prove this one theorem, that if we have U1 and UM subspaces, then when you take the sum, you continue to have a subspace. And the other nice property is that the sum is the smallest subspace contained U1 through UM. So there is no smaller subspace that contains all of U1, U2 up to UM. Now this is a nice theorem because part A also gives you another example of checking whether something is a subspace or not. We just use the 3 conditions of checking for a subspace. So the first thing that we have to check, right, is that the 0 element is inside of U1 through UM. Well, that part is actually pretty straightforward to check because 0 is in the sum, since 0 is in UI for all I, because each UI is a subspace, and we take the sum of those guys. So 0 in the first one, 0 in the second one, 0 in the third one, all the way up to 0 in the last one, gives me 0, which is the sum of 0, and this is an element inside of the sum. Okay, so the 0 element definitely belongs to the sum of these subspaces. Now we have to show that if we take any 2 vectors inside of the sum, the sum of those 2 vectors continues to be in the sum of the subspaces or subsets. So for 2, let x and y be inside of u1 up to um. Right? So we pause and say, well, what does it mean for this to be true? So x is equal to a sum of m things with xi in ui, and the same thing for y. Y is equal to y1 up to ym with yi inside of ui. Okay, so now we take these 2 vectors and we add them together. So then x plus y is equal to x1 up to xm plus y1 up to ym. And now because we're inside of a vector space, addition commute. So I can regroup it any way I want. So I have x1 plus y1 all the way up to xm plus ym. So I've grouped the xi with the yi. Right? Now, since xi and yi are inside of ui, and ui a subspace, we have that xi plus yi is inside of ui. Okay, so each of these pieces are in the right spot. This is in u1, the second guy would be in u2, and so on. So we get the result that we want, right? So x plus y is going to be inside of u1 up to um, because each of these individual pieces are in the set ui. So that tells me that I have closure under addition. And finally, let's talk about the closure under scalar multiplication. So it's the same sort of idea. So we take x inside of u1 up to um, and I take some sort of scalar in f. I remind myself what it means to be in the sum. So x1 up to xm. X is equal to the sum of x1 up to xm with each xi in ui. Then if I take c times x, that by definition is equal to c times x1 up to xn, and then by properties of a vector space, we have this is equal to, by the distributive property, this is equal to cx1 up to cxn. And now this element here is inside of, this should be an m, and that should be an M, and inside of U1 up to UM, since CXI is inside of UI for all I. And the reason this happens is because UI, maybe I'll put it right here, since UI is a subspace. So that individual set is closed under the properties of scalar multiplication. So the three conditions to tell me, and I think I have enough room here, is thus U1 up to UM is a subspace of V. Okay, so the sum of, if you start with a collection of subspaces, their sum continues to be a subspace. So give you a chance to look at that for a second. And we scroll back. So we've taken care of part A. And what about part B? Okay, that this is actually going to be the smallest. All right, so first of all, we note that UI is definitely inside of U1 up to UM. Okay, so try to convince yourself of that, but each of these UIs are inside of the sum. And now, suppose that we have another subspace, U1 up to UM is contained inside of some other subspace, W. Then for any little UI in capital UI, we have U1, U2 up to UM are also inside of W, right? But W is a vector space. But W is a subspace. So it has to be closed under addition. So U1 up to UM is inside of W, right? So thus the sum would also be contained inside of W. Okay, so this is the sum of, these should be capital U's, so that make them a little bit bigger, so that the sum of these subspaces is inside of W. So this actually proves what we needed to do, because U1 through UM contains all the UIs, and if you took any other subspace that contained all of these sets, it actually has to contain all the sum of those subspaces as well at the same time. So that's what the theorem is telling you, and that kind of finishes off the proof. Okay, so just to maybe go back, kind of reinforce some of these ideas, is here's an example. In this example, both U1 and U2 are subspaces. So here's U1 and U2. This is the sum, so this is a subspace. And this plane is actually the smallest subspace that contains both U1 and U2. So to finish today's lecture, here are some of the key ideas. We learned about subspaces, we learned about the three conditions for a subspace, and we learned about sums of subsets and subspaces. And that's it for today. I'll see you in lecture 4.